So, this is my first time going live on Facebook. So this is the first video in a series on emergent gravity. Emergent gravity is, you can think of it as related to quantum gravity because it's attempting to solve the same problem. So what I want to do first is I want to sort of like translate thermodynamics into information theory, and I also I realize that most of you don't have like a very advanced math background, so I'm going to be getting into some advanced math concepts. But I'm going to try to break it down in a way that's accessible to a wider audience. So if you look at my article that sort of goes with this lecture series, you probably won't be able to follow it. And when I wrote it, I sort of had a sense that maybe 10 people on the planet could follow 100% of it. So really this is going to be kind of a elaborate process of breaking things down. So where I want to start is with the first law of thermodynamics, which I've written out here. And what I need to do is I need to break down each of these forces and explain what each of them means. So we have sort of two perspectives here. We have the thermodynamics perspective, which is highly relevant. It's basically explaining how so much of our society runs. Like the combustion engines that you use to get around your planet is basically running off of thermodynamics. And then contrastingly, so much of our society runs on the internet now, which is all related to information physics. So if you want to Google like Shannon's entropy and all of the topics related to that, that's where you get this crossover between information physics and thermodynamics. And in emergent gravity, they're pretty much the same thing. So in emergent gravity, basically you have the theory that thermodynamics is, in a sense, powering quantum gravity, much like an engine. Not exactly like an engine, but you can think of quantum gravity almost like an engine. So where we should start is with temperature. Like an example, so you have a boiling cup of tea, and you'll notice that the steam is coming out of the tea and into the room. And you probably have some intuition that the temperature in the room is lower or smaller than the temperature of the boiling cup. And so what happens then is that the heat flows out of the cup and into the room until such a time as the cup reaches room temperature. And then when the cup reaches room temperature, we call that thermal equilibrium, and that's when the heat flow stops. So you have that exact same concept happening in emergent gravity. So I'm going to write out an equation here for temperature. Let's see, dE ds x. And we really need to start with temperature because it's sort of the most fundamental thing, maybe with the exception of entropy, to thermodynamics. So I wrote this equation here. This is for temperature. Now, these differentials here, basically, that's the rate of change between energy and information. And, well, S is representing entropy. And I think of entropy as almost interchangeable with information. And I'm going to explain what I mean by that. And then here, these subscripts are basically saying that the position, volume, and number of elements are held constant. And so that's why you have these sort of curly D's instead of the usual differential D that you see in calculus, or, you know, like entry-level calculus. So you have these curly D's to indicate that there's other variables. There's other variables here that are being held constant. So the temperature is a rate of change, or related rates between energy and entropy. So it basically tracks, well, how does energy change when entropy changes. So if you're at the algebra level, in math, if you're at the algebra level, I want you to look into related rates, and I want you to look into slopes of lines, linear equations, and if you read up on these, that will at least give you some intuition of related rates. So another way to think of it is like a conversion factor between entropy and energy. So like an example would be like if you go to the dollar store, the items it costs $1 per item, right? So your rate would be $1 per item. So then you take the number of items that you're purchasing and multiply that times $1, and then that converts the number of items over into the cost of the items, right, before tax. So that would be like an example of how you would use related rates in the everyday life. So temperature basically converts your entropy over into energy. So how much energy can you get from the entropy changing? And then the first law equation that I've been discussing here, these entropy terms here, that converts the energy from the entropy flow into these other forces here, which I need to discuss what these other forces are. But basically you can see that the energy changing can convert the temperature and entropy, which we call heat. So the heat flowing, we can convert that energy into other forces. So the first law equation is basically tracking the flow of energy from heat into all of the other forces. And so really the first law equation, it's really an equation of conservation of energy, in a sense. Conservation of energy is basically in every field of physics. It gets broken a little bit by relativity, but that's beyond the scope of this video. But in most areas of physics, the conservation of energy applies, and especially in thermodynamics. Basically, this adds up the total changes of forces that perform work, and then when you add them up, then you get the total change of energy of your system, which would be dE. In emergent physics, we're basically thinking of the heat or temperature as driving the other forces that are performing work. So when you have an engine in your car, basically you're burning the fossil fuel, And when you're combusting the fossil fuel, that heat provides pressure, which pushes on the pistons. And then when the pressure moves the pistons, then you can convert that motion into mechanical work, and then you convert that work into kinetic energy on your car. So basically, you burn the fuel, and then thermodynamics happens, and then you convert that mechanical work energy into kinetic energy. So basically, when you push on the accelerator of your car, it's converting fuel into kinetic energy, and then that's why your car changes speed, right? So that's basically thermodynamics in a nutshell. Now, another good example that I was thinking of how to explain what temperature is. So when you have a thermometer, like the old school mercury thermometers, so you put this in like your cup of tea or whatever, right? Continuing with the tea analogy. So you put the thermometer in your cup, and what happens is the mercury rises to the level of where the marks of temperature are. So basically, you're performing a measurement on the temperature of the cup, right? So now, what's driving the mercury up? Well, it's the tendency of the cup to reach thermal equilibrium. So the cup is attempting to reach thermal equilibrium. Well, not really like attempting, but you can kind of get a sense of what I mean here. Like statistically, the cup is reaching thermal equilibrium with the room, and so that is sort of driving the heat energy into the little metal piece at the bottom. And then when the heat energy enters, it performs mechanical work on the mercury. So that heat energy leaves the cup, enters the mercury, and then it provides pressure, which is a type of force, which expands the volume of the mercury. And then when the mercury rises, then you can get a measurement of the temperature, right? So that would be, already we're getting into an example of what pressure means. That's this term here. So basically the thermometer is converting, so here you have two temperatures, right? You have the temperature of the cup, and you have the temperature of the thermometer. And then because the temperature of the thermometer is less, it pulls this entropy into the thermometer, and then when it pulls the entropy in, then it performs work on the mercury in the form of pressure. And then the pressure changes the volume. So that's why you have a dV, V for volume. The pressure changes the volume of the mercury, and then you can perform a measurement of T1, since the heat flows from T1 into T2, right? And then that happens until it reaches thermal equilibrium. And then that's when the measurement is concluded. So to talk about temperature, we really need to talk about entropy. Now, entropy is I feel like I should just cut the video now because we're already 14 minutes in. So I might want to let you kind of chew on that for a while. Come back to me with questions in the comments. And then next, I think we should talk about what entropy is. You can also do some searching on Google to kind of get a sense of what entropy is. So that's what I'm planning for the next video, is to discuss what is entropy. The changing entropy is really what is driving the first law of thermodynamics. The changing entropy is what allows you to convert the heat into other forces. So the TdS term Let me at least get started here. dq is equal to T ds. So this is the dq here. This is the change in heat, which is equal to the temperature times the change in entropy, and that change in heat is what is getting converted into the other forces in the first law equation here. So the heat is basically getting converted into work. So that's sort of a hint of what entropy is. Basically, the entropy relates heat, which you can measure in joules. Usually it's measured in joules or kilojoules, and you can change that heat energy over into work. So basically, do some Googling and come back to me with questions on temperature. Start getting a sense of what entropy is, and we can cover that in the next video. Okay, have a good rest of your day.